Hey everyone, my name is Greg. I'm going to tell you about this paper called Epic Fail: Emulators Can Tolerate Polynomially Many Edge Faults for Free. This paper is in the upcoming ITCS in 2023, and it is joint work with Mike Dinitz, who's at Johns Hopkins, and with Yasamin Nazari, who's at the University of Salzburg. Okay, so I'll start by telling you what objects we're going to be talking about. An emulator is defined as in this gray box. At a high level, you can think of an emulator as a tool for sparsifying a graph, getting a much smaller space or simpler representation of that graph, while approximating its distances. So specifically, an emulator of an input graph G is an undirected graph, but it can have edge weights if you like. It is some different graph H, with the property that the distances in the emulator are a multiplicative k approximation to the distances in the original graph. For example, if this is your input graph G, and here we'll imagine that it's unweighted or that all of the edges have weight 1 if you like, this other graph here is an emulator H, and the reason why it's an emulator H is because if you look at any two nodes in the input graph, and you look at the corresponding distance between those two nodes in the emulator, it's at most 3 times the distance in the input graph. For example, for these top two nodes, the original distance is 1, and in the emulator it is 3, which counts. So emulators are allowed to have edges that are not present in the original graph, like this long-range red edge right here. And in principle, you could choose any weight that you wanted for that edge. But in fact, this is not a real choice that you have to make. Without loss of generality, it is always the right decision to set the weight of one of these new emulator edges to be exactly the distance between its endpoints in the original graph. So here, when we are choosing the weight to attach to this red edge, we have to choose it to be at least 2. The reason is because the distance between those nodes in the original graph is 2, and this lower inequality in the definition says that the distances in the emulator need to be at least as large as the distances in the original graph. And meanwhile, there is no advantage to choosing the edge weight to be larger than 2. Once we satisfy this, we want our distances in the emulator to be as small as possible, so we would just choose to set it to be 2. So without loss of generality, we're basically just choosing an edge set for our emulator, and then you can think of the weights as happening automatically as the distances in the original graph. And as I was saying a second ago, the goal in emulator construction is generally to get a favorable trade-off between the size and the stretch. So in other words, you would like there to be as few edges as possible in the emulator relative to this parameter k, which is measuring the amount of error that you take on by using the emulator. To give an example of the sorts of theorems that people prove in this space, this is a classic theorem by Althofer, Das, Dobkin, Joseph, and Soares from 1993. It says that every n-node graph has a 5 emulator on order n to the 4/3 edges, and this is best possible. In other words, there are some particular input graphs where if you want a 5 emulator, you must pay omega n to the 4/3 edges. You can't do any better. Okay, so that's what an emulator is. I'm actually going to talk a little bit about applications early. The applications are going to play a major role in pointing us towards the theorem that we'll be working with in our main results. One common type of application for emulators is as a pre-processing step for approximate distance computation. So in other words, if you want to compute shortest path distances in your input graph, and you're okay with a bit of approximation in that computation, something you might do is first pass to an emulator which has a little bit of error in its distances, but it's much sparser, and so your algorithms will run faster on that emulator. That can often be worth it. I won't talk too much about those applications, though. What I actually want to talk more about are these applications in networking, specifically to this thing called overlay networks. So let me tell you what an overlay network is, or at least sort of a theory cartoon of what overlay networks are that will motivate what we're going to talk about. So you think of yourself as getting some kind of base network G on input. Very often it's the internet. That's a common thing that overlay networks are applied to. But we'll use this little example in the bottom left. And once you have this base network, your goal is to carefully design yourself an overlay network. An overlay network is over the same vertex set, but you can choose any edges that you want. You can choose some edges from the original base network if you want. You can also choose some different long-range edges like these thick red edges here that are not corresponding to edges in the original base network. But the difference here, to be clear, the base network is an actual physical network made of physical nodes and links. And the overlay network, meanwhile, all it is a pair of node pairs, as a set of node pairs stored in memory. So base network is a physical thing. The overlay network is just a purely like logical set of links stored in memory. But the goal of the overlay network is to basically let yourself have the illusion that the overlay network is the original network. You'd like to be able to like perform routings on this overlay network or pass messages along it and have the routes that you choose in your overlay network get seamlessly resolved into actual physical routes in the base network along which information can be communicated. So specifically, you might define routings along the overlay network. And what happens is that there's some very efficient protocol that is interfacing between the overlay network and the base network that will resolve the routing you choose into an actual shortest path in the base network. Specifically, it will resolve each edge along the path that you choose into a shortest path between those endpoints. So for example, if you were to try to route along this chain of two thick red edges, it would resolve into this dotted red path where each of the two red edges is being resolved into a chain of two edges between its endpoints. Okay, so that's how overlay networks work. One nice thing about overlay networks is that you can think of the design of overlay networks having exactly the same quality as we were just talking about emulators having a moment ago. You are choosing the edge set in the overlay networks, and then the weights of all the edges that you choose get basically automatically set for you. In other words, as soon as you choose this thick red edge to appear in your overlay network, the routing protocol is always going to resolve it into a chain of two edges. And so it's kind of like the weight of this edge automatically becomes 2, and there's nothing you can do about it. It just gets set to the distance in the underlying graph. So that's one point of similarity. The other point of similarity is that you often have the same goals in designing an emulator as you do in designing an overlay network. Specifically, you generally want your overlay networks to be sparse or simple so that there's an advantage to working with these instead of directly with the base network. And additionally, you want the distances in your overlay network to be not too much larger than the distances in the original network. In other words, if there's like two adjacent nodes that can talk to each other very quickly in the base network, it would be kind of bad if then the shortest path between those nodes in the overlay network was a million times as long. You'd be introducing a lot of latency between those nodes, and that would be too big of a penalty to make using the overlay network worth it. So together, these two goals are exactly like saying that this automatically weighted overlay network is a sparse K emulator of the input graph. Okay, so that's the tie between overlay networks and emulators, and we're going to run with it. One thing about networking applications is that parts can fail. It's very common for nodes or edges to go down temporarily and need repair, and everything else still has to run smoothly around them. This introduces this additional constraint in applications, which is that an emulator can be unusable if these failures could completely destroy its stretch properties. Let me give you an example to say what I mean. Here's our input graph and emulator from before. We'll look at this specific pair of nodes UV. Originally, the distance is 1. In the emulator, the distance is 3, which is totally acceptable. A 3 emulator is fine. You're willing to take on times 3 error. However, let's now imagine that this node fails. This node named F goes down temporarily. So now the distance between U and V in the original graph is still 1, but the distance between U and V in the emulator is now infinity, because as long as this node has failed, it's just disconnected. So suddenly, if you need to be concerned about these failures, you really regret using the emulator, because these two nodes that used to be able to talk to each other now can't talk to each other at all, and that's not worth it. So this motivates, and I'll make this formal in a moment, but this is motivating a different type of definition that we could work with that would be an emulator that has good stretch properties and which still has good stretch properties after these failures. So for now, I'm just going to sort of vaguely say this 3 emulator H that we came up with, it is not a one vertex fault tolerant 3 emulator of the input graph G. And the reason is because there exists at least one vertex that could fail in such a way that the remaining part of the emulator is not a 3 emulator of the remaining part of the input graph. Okay, so that's good. we now sort of see what could generally go wrong, let me work towards making this definition more formal so that I can tell you results about it. This basic model of fault-tolerant emulators was introduced by the same set of authors, me, Mike, and Yasamin, at ITCS last year. And it's directly motivated by this overlay network application, but here's the idea. So base network edges can fail. Those are the ones that correspond to physical links that could go down. These failures don't affect the edge set of the overlay network, no matter what. Remember, the edge set of the overlay network is just a set of node pairs stored in memory, and that can't break. Even if a physical edge breaks, that node pair is still sitting there in memory. But what does happen when these base network edges fail is that this protocol that resolves overlay network edges into shortest paths in the underlying graph, that protocol needs to get updated in light of the failures, and that can change the weights of the edges in the overlay network. So really what the effect of edge failures is it is not a change in the emulator edge set, but it is a change in the emulator edge weights. So this set of three graphs here in the middle is an example of what I'm talking about. In this original graph on the left, this thick red emulator edge would have weight 2, since that's the distance in the underlying graph between these endpoints. Under the two edge failures that are marked in the middle, the effect that that would have is that it would cause the weight of this edge to update to become 3, since after the failures, that's the new shortest path that the edge will get resolved to in the overlay network resolution protocol. And similarly, if these two edges instead were to fail, then the weight of this emulator edge would get updated to 4. Okay, so with that in mind, here is exactly the same information as on the previous slide, but now it's a fully formal definition. So this is the definition we use. We just say that an F edge fault tolerant K emulator, it is a graph H, which is the emulator, so that for any set of failing edges, if you were to compare the distances in the failed version of the input graph, that's G minus F here, and you compare those distances to the distances in the emulator under the weight updating associated to those failing edges, then you get a K approximation. So another more informal way of saying what's going on in this definition is that for any set of failing edges F that we might need to consider, so size at most F, the overlay network distances are still a times K approximation to the distances in the failed version of the base network G minus F. Okay, so that's the definition of emulators with failures. I want to make a quick note that if you are familiar more with the algorithmic applications of emulators than the networking applications of emulators, you might be objecting to this definition. It might feel wrong to have this like automatic weight updating behavior. And I would totally understand that. We are not really claiming at all that this is a reasonable definition of fault tolerance for the algorithmic applications of emulators. We are really only claiming applications in the networking sense. So I just want to sort of quickly say, this definition is, I think of it as being a networking only sort of thing. Okay, so anyways, with that setup in mind, here is the results that the same set of us three authors proved last year. We were specifically studying vertex failures, and we proved that every graph has an F fault tolerant, F vertex fault tolerant 5 emulator with this many edges. And I've separated this out into two parts. This purple end of the 4/3, I'm going to call that the base cost. It's the base cost because omega n to the 4/3 edges are needed for even a non-fault tolerant 5 emulator. That is known to be tight. So we're going to have to pay that n to the 4/3 no matter what. The more interesting thing to look at is what is the price of fault tolerance. So that's this O tilde F to the 1/3 term right here. That O tilde is hiding log n factors. But what it means is that like really the price of this vertex fault tolerance for emulators, it's this. You want F vertex fault tolerance, you pay a factor of F to the 1/3. So this turns out to be tight. Up to these hidden log factors, you can't do any better. But anyways, edge failures are what we are looking at now in this current paper that I'm talking about. And for exactly the same reason, you're going to have to pay this n to the 4/3 term. The only question is, what is the price of fault tolerance that we're going to need to associate here? Is it going to be more than this F to the 1/3? Is it going to be the same? Is it going to be less? It's not really clear, and that's the question to investigate. And it turns out that the answer is this. The answer is that the price of fault tolerance for F edge fault tolerance in emulators, it is constant. And this is really surprising. We are saying that it is a constant independent of both n and f, with the only extra condition dimension being this, is f needs to be at most this moderate polynomial. So specifically, the base cost is n to the 4/3. The price of fault tolerance, as long as f is not too large, is free here. So now we can go back to this subtitle of this paper, which is Emulators Can Tolerate Polynomially Many Edge Faults for Free, and point at what it means. It's pointing at the fact that like the extra factor that you pay is actually independent of f. It's just a constant. Okay, so I think this is kind of surprising. Let me state it in a different way. So the main result for 5 emulators is that for any n-node graph and parameter f, which can be up to n to the 2/9, there is an f edge fault tolerant 5 emulator on n to the 4/3 edges, and you can do no better than this even for non-fault tolerant emulators. Meanwhile, a natural question that you might have is, how much bigger can this f be? Could we take this range n to the 2/9 and push it up a little bit higher? The answer is maybe. All that we are able to prove in this paper is that you're not able to push f beyond n to the 1/3. If f is larger than that, fault tolerance is definitely not free anymore. But there is a gap here, and closing that gap is one of the open questions that we're leaving. I'll say a little bit more about that at the end. Okay, so let me give you a couple of proof ideas. This picture is a router on fire, which I don't know, I'm a theorist, but I assume that something like this is what's happening when you need fault tolerance. Anyways, so in order to say the proof ideas, let me quickly try to say what is the proof idea in the non-fault tolerant setting. So this original result by Altofer, Das, Dobkin, Joseph, and Suarez from 1993, where they said every n-node graph has a non-fault tolerant 5 emulator on n to the 4/3 edges. Let me say quickly how that works. So their proof strategy is to very carefully construct their emulator so that it has girth greater than 6. As a reminder, the girth of a graph is the smallest number of edges in any cycle. So this is the same as saying that it has no 3, 4, 5, or 6 cycles in it. And after they do that, they use this lemma from extremal combinatorics that says that any n-node graph of girth greater than 6 can have at most n to the 4/3 edges. So that constrains the size of their emulator. The way that they did this, the way that they constructed H to have high girth is with this really simple and really clever greedy construction algorithm. So specifically, I'm going to show you a picture of this in just a second, but they start with H being the empty emulator. It's on the same vertex set as the input graph, but with no edges at all. And then they are considering the edges of the input graph in order of increasing weight, and they add the edge to the emulator if it's currently necessary. And what we mean by if it's currently necessary is if the distance between the endpoints of the edge is more than 5 times the weight of the edge. In other words, this node pair UV that are the endpoints of the edge currently violates the emulator inequality that it needs to satisfy. And so therefore, we'd better add the edge to fix that. So here's a quick picture. Imagine this is your input graph G. H, which we are going to design to be a 5 emulator, starts out with no edges, but over the same vertex set. We consider the edges one at a time. When we consider this, the distance in the input graph is 1. The distance in the emulator is infinity currently, since they're disconnected. So we would take that edge into the emulator. Then we consider the next one, take it by the same logic, consider the next one, take it, consider the next one, take it. Finally, we consider this last edge. Here we notice that the distance between these nodes in the original graph is 1, and the distance between these nodes in the emulator is 3. There's this path of 3 edges that we already added. And so therefore, we already have better than a 5 approximation between U and V in the emulator. And this edge UV is not currently necessary in the emulator. So we would instead reject it from the emulator at this point. So this is specifically the 5 emulator that would be built. I'll say 2 things about it. One is that you might notice this is actually doing something more specific than producing an emulator. It's producing a spanner, which is a special type of emulator that is a subgraph of the input graph. The other thing is that you can notice that this 4 cycle in the input graph didn't get closed in the emulator. We rejected its last edge. And if you want to see why this results in emulators of high girth, you can kind of convince yourself through similar logic that it will never close a cycle of length 3, 4, 5, or 6. So therefore, its girth will be greater than 6. Okay, so that's the basic idea. To very quickly say what we are doing, one of the most surprising things, I think, is that we are actually using a similar greedy construction algorithm in order to build our fault-tolerant emulators. So right off the bat, I'll talk more about this algorithm in a moment, but we are going to produce emulators that are a subgraph of the input graph. So another way to say that might feel very strange if you're familiar with this area, that like we are claiming an advantage to using emulators, and yet the emulators that we build are subgraphs of the input graph. In a way, what we mean by that, we talk more about this in the paper, but what we mean by that is that uh, the power that we are gaining is from the model of fault tolerance changing in the world of emulators, more so than the freedom to add long-range emulator edges in our construction. But anyways, the algorithm that we're using is basically the same as the one before. We start with H being the empty emulator. We consider the edges of the input graph one by one, and we add it to H if it's currently necessary. The only thing that's really changing is the meaning of if currently necessary. Before, if currently necessary was just if the emulator inequality was violated over the endpoints of this edge UV. Here, we need to say like it's violated if there exists any fault set F that is a valid fault set, it's not too large, in such a way that the emulator inequality is violated in the reweighted version of the emulator. So this is a bit more of a technical thing to chew on here, but you can just think of it as saying like, if you can prove, given the current state of the emulator, that it's safe to throw away the edge, then go ahead and throw away the edge. If you can't prove that, you'd better take the edge into your emulator to be safe. So at a very high level, the way that our analysis works, and things get technical very fast, I'm not going to say much about it here. We're using the blocking set method, which is a strategy that's been used in the last few papers in this area, but it formalizes the following intuition. A moment ago, we were talking about a similar greedy algorithm, and we showed that it has girth greater than 6. This is different, and so it is not still true that the emulator we produce is going to have girth greater than 6, but just at a very fuzzy intuitive level, because we are using such a similar algorithm, it might feel like the emulator that we produce should be close to girth greater than 6, whatever that means, like it is structurally similar in some key way to a high girth graph. And after that, it might also be intuitive to say any graph that is close to having girth greater than 6, again, whatever that means, should have close to order n to the 4/3 edges. So my hope is that these two bullet points make sense at this fuzzy intuitive level. The way that you formalize these two bullet points is using an object called blocking sets. It's kind of like saying your graph can have cycles of length 6 or less, but they admit an unusually small hitting set or something like that. The actual definition is much more technical, so I'll refer to the paper there, but this is the intuition behind what we're doing. Okay, anyways, here's another picture of something that presumably might go wrong that might cause you to need a fault-tolerant emulator. But I'll just sort of say our generalizations and wrap up the talk here. So here is the, we were sort of focusing on 5 emulators just to have a simple example to keep in mind through this talk. Here's the more general non-edge fault tolerant theorem that was proved by Altofer, Das, Dobkin, Joseph, and Suarez in 1993. It says for any positive integer k, every n-node graph has a 2k minus 1 error emulator on n to the 1 plus 1 over k edges. And moreover, this is best possible if you're willing to assume this thing called the girth conjecture, which is popular in the area. Anyways, where our main result for odd k is a positive result, we are able to prove that for any odd k, a similar phenomenon to what I was just talking about for the case of 5 emulators, which corresponds to k equals 3, does in fact hold. So for 5 emulators, we got free fault tolerance up to f to the 2/9. For any odd k, you can have free edge fault tolerance for 2k minus 1 emulators up to some polynomial. So this is good. We get polynomial amounts of free fault tolerance for all odd k. Interestingly, something very different is happening for even k. For k equals 2, so in other words, emulators of stretch 3, since you're plugging 2 into this 2k minus 1 term here, we can completely refute the possibility of free fault tolerance. We prove this is a lower bound, this like you need f to the 1/2 times n to the 3/2 edges. And that suggests that if f is a moderate polynomial, or any polynomial at all, I mean, you're already paying more than what is promised in the non-fault tolerant case. So this phenomenon that exists for odd k, it definitely doesn't exist for k equals 2, And for even, that should be even k strictly greater than 2, like so 4, 6, 8, and so on. It is an open question whether or not there is free edge fault tolerance at all. We were not able to resolve it. The only thing we can say is that if the number of faults is strictly like asymptotically larger than n to the 1 over k, there's no free fault tolerance, but below that, it may or may not exist. And we're leaving that as an open question that I think is really interesting. Okay, so I just mentioned some open questions. Here they all are on one slide. This is one that I mentioned earlier. One thing that I think would be a good follow-up use of time that I'm interested in seeing resolved is to settle the range of free edge fault tolerance for 5 emulators. We are able to prove that if you have n to the 2 over 9 faults, it's free. You don't have to pay anything extra. And if you were to have asymptotically more than n to the 1 over 3 faults, it is not free. Then you would have to pay something above this n to the 4/3 term. And closing that gap, or figuring out what is this value of this constant c sub 3 that determines the threshold of free fault tolerance, it's a very interesting open question. Another open question is to improve the range of free fault tolerance for 2k minus 1 emulators when k is odd. In general, the range of free fault tolerance that we get for some choice of odd k, it falls in this range. It is omega 1 over k squared, and it is at most 1 over k, but we don't know what the right value of the constant is within this. So trying to improve our understanding of when fault tolerance is free for emulators when k is odd is an interesting open question. And probably the hardest, but also most interesting open question of all is this one. Is there any free edge fault tolerance for 2k minus 1 emulators when k greater than 4 is an even number? Can we get a similar phenomenon to what was going on with the odd case for the even case, except for k equals 2, where we know it's definitely not going to work? Okay, so these are open. I would love to talk with anyone about these who is interested. Here's just a quick wrap up. The model of edge fault tolerant emulators that we are working with, it has applications in networking, but not really in algorithms. This is really focusing on the overlay network application in order to be justified. The main result, which I think is very surprising, is that you can get resilience to polynomially many edge failures while still only paying a constant factor in your emulator size for that power, which is much, much stronger than anything else that has shown up in similar questions in this area. The last thing is just that the exact amount of free fault tolerance is still very open. Those last 3 open questions that I mentioned are all about pinning this down. So thank you for your attention. And here's one last thing that I suppose could go wrong with a computer that would cause you to want to read our paper. So I hope you do. I'm happy to talk with you about it. And if anyone's at ITCS, I'm looking forward to seeing you there. Thanks, everybody.